So we're facing the problem of putting a conditional probability distribution on tree generation actions that would give us a probabilistic grammar that we could use to put probabilities on trees. If we had that, we could put probabilities on strings as the sums of probabilities on possible trees, and really open the door to using the deep learning toolkit to learn probabilistic models to put over these explicit hierarchical symbolic structures. So in thinking about doing this, let's take into account what are the possible next steps in an action sequence given a context, and note that there's many of them. So for example, in this context, we could do any of a number of things. The next thing that happens might be that we would generate a new terminal symbol away inside the VP. Alternatively, we might close the VP off entirely, say that change is its only daughter. We might generate a prepositional phrase, which would become a new open node inside the verb phrase and get onto the stack. We might instead generate a new open noun phrase, and so forth. So there's a variety of different things that we might do. The general problem is that we need to characterize this conditional distribution probability of action on context. And the question of how we use the context is entirely going to be the question of, well, how do we actually do integration of deep learning techniques with this incremental symbolic structure generation process? So we're going to take these neural models and we're going to use them on the context in some way. So there's a variety of ways we could do this. Note that here are the resources that we have. We need to integrate them some ways as inputs and use some kind of neural generalization to then put a probability distribution on actions. So the actions themselves are going to be the outputs. The inputs are going to be the context in some form, and the outputs will be actions. And as the exemplar of a good general purpose tool, we'll be looking at the LSTM, which we've seen before, as the neural generalization tool. So here are several options that we would have for how we would apply this neural generalization to the action prediction problem. So one might be that we would just actually do what we did before. We would run the recurrent neural network model over word sequences in the context as normal, but instead of predicting next words, we would predict next tree generation actions. So in this view, it would be these words that have already been generated by the action sequence that would then feed in as inputs to the LSTM language model. The predictions note, so the prediction of the next action would be, in the first couple of cases here, we would have predicted cat after generating hungry, but then the next thing that we would predict after cat would not be another word, but it would be a reduce action. So both word generation and non-word generation tree actions would have to be predicted. Now, we would continue on doing this. This, however, will not work well at all. And I'm going to leave it as an open question for you to think about, why would this not be a good idea, just to run the model over only the word sequences and nothing else? So that would be option one. It's not a great option. Here's another option. We could run the recurrent neural network model over tree generation actions themselves. So we would actually take this action sequence as the representation of the sequence that we're generating actions given context on. And so the context is simply the sequence of previous actions. So just to horizontalize this and show you more explicitly what this would look like, let's look at this horizontal representation of the action sequence. Remember, there's a one-to-one correspondence in this representation of trees as strings between tree generation actions and appending things to the string. So this is the sequence of actions that has led up to this point, and we would simply, each of these actions would feed in as an input to a recurrent neural network model. The model will be trained to predict the next actions and so forth. So this actually is a model that was developed and tested. This is Cho and Charniak's model, 2016. Now, there's actually an inferential challenge that this raises. And to understand that inferential challenge, let me pose the following questions. Suppose that this is, we already know that we have this preceding tree context. So we have S goes to NPVP, NP went to I, and VP started with saw, but it may not be done yet. And we know that the next word is the. So what are the different ways we could get from this incremental tree in the context that I've underlined in blue to the next word the? There has to be additional tree structure that would connect it. Okay, I mean, it's possible that the would be generated as a daughter of the VP directly, of course, but it's more likely that the would be inside a noun phrase. But even if it's inside a noun phrase, there are many different ways that it could happen. So for example, it might have been that, that first we generated an open node NP, and NP had as its first daughter the terminal the. This would be consistent with, for example, a continuation that might look like I saw the child. that's the whole sentence. But there are many different ways that it might look. So for example, we actually might have multiple nested noun phrases that are generated before getting to the word the. So for example, the child itself, if that's a possessor, the child, as in I saw the child's dog, then the child should be an NP, which is inside this larger NP. And so the tree structure would be that you would have to generate incrementally on this tree generation algorithm. You'd have to generate both of these noun phrases. So in order to be able to ultimately deal with continuations like I saw the child's dog, I would have to actually generate multiple NPs at that point. Alternatively, saw can also introduce a complement clause, not just a direct object. So for example, I saw the child leave actually has to have the structure that a sentence has begun here, and then its subject begins. And so this is a third tree structure, and we can imagine combinations of these things. So for example, I saw the child's dog leave would have to have yet another structure. I saw the child left has yet another structure. I saw the child's dog left, and so forth. And notice that because of this left recursive noun phrase opening possibility, there's now actually a potentially unbounded number of tree generation operations that you would require just to get to the next word. So we actually, in principle, can't even enumerate all the possible incremental trees that might be hanging over an actual word sequence. So there's uncertainty about this structure, and doing this processing left to right requires management of that uncertainty. And so here's the classic one of the classic ways of dealing with this, which is what's called beam search, which we keep only a set of good possibilities open. And to understand how beam search works, let's imagine the following situation. We take that one tree context and we think of all the different possible action sequences that we would require to get to the word the. This is a non-exhaustive list. And now if we have a probabilistic model, each possible action sequence from the context will have a probability. Okay, and so we can use the probabilities of those possible action sequences to prioritize the possibilities. And so if below we have the different log probabilities, for example, of the actions given the context, we can put sequences with higher log probability as higher priority, and then we would say, well, we're only going to keep a finite set of these, and we might choose plausibly to choose only the best ones. And so these two we would just not keep, but if we had a beam size of 4, we would not keep these, and we would keep the other 4. But we would actually have to do this simultaneously for multiple contexts. Typically, there will be multiple tree structures that are possible for the context. And so we'll have multiple contexts, multiple action sequences for each context. We can use the conditional probability of the action given the context, and we can also score the context. And we'll wind up with a joint probability or joint score for the incremental structure, and we can maintain those using a beam. So that's an inferential challenge for any model that's going to include, that's going to maintain multiple possible candidates. And beam search is one method for maintaining that uncertainty and managing it. So that was option 2, and we would need to deal with that uncertainty for option 2 because we had these latent sequence representation elements during inference that we have, not just the actual words. Here's another option, option 3, which is we could actually run the recurrent neural network not only over the only over the stack or over the action, we could also run it over the stack. So we could try to generalize from the stack in some interesting way. And this will look something like running the RNN over the action sequence, but it's actually different. So how do we do this? So conceptually, what we want to do is we have these, this is a set of 4 stack elements where the delimiter is this vertical bar. And so we want to take a model and say an LSTM and run it over this and use it to predict the next parser action, the next tree generation action. And this looks fine. Of course, as in all these models, we want to learn embedding representations for all these elements and use them so that we can generalize over elements that have similar behaviors and so forth. But you'll recognize that there's a problem, which is that for some of these elements, there's sort of atomic elements in the grammar and vocabulary. So S, VP, and chaste, there's a finite number of these. Chaste is a vocabulary item. S and VP, there's only going to be one of those open bracket symbols for each non-terminal that exists in the vocabulary. But for the hungry cat, we have a problem because this is something that's constructed on the fly. And this representation, this phrase may never have occurred in our training history. It may never have occurred in the history of the universe. So we have to have some way of computing an embedding representation to feed in to the LSTM at this point. So how do we do that? These have to be computed on the fly. And so a really cool approach that was introduced in papers by Dyer in 2015 and 2016 is to run an LSTM in a recursive fashion. So recursively, when you compose a phrase, you actually will run an LSTM over the elements of the phrase from left to right and from right to left. This is what's called a bidirectional LSTM. And then you take the ones from right to left and from left to right. You concatenate the two, so these are two parts of a single vector. And then this vector itself becomes the embedding representation. So this vector that goes in as the embedding representation per phrase is computed on the fly, and that allows the model to behave compositionally and productively. Okay, so you may be asking, well, how do I know what values to compute? This is all computed via backpropagation. It's all the weights. There are weights in this LSTM. So the weights in this model are trained via backpropagation as traditionally. So you will get information every time that there is good or bad prediction of a parser action sequence. There is the possibility of updating the weights backward through this now interesting hierarchical structure, because the decisions about how to compose this phrase now have played a role in this parser action up here. So that approach is the basis of what are called recurrent neural network grammars. And in fact, actually, the original recurrent neural network grammar paper used all three of the options together. It did neural generalization over the word sequence, over the action history, and over the stack representation with this compositional operation. And then it just concatenated the three, and the concatenation of the three becomes a vector that you can use for prediction of the action sequence right here. And so that's one very interesting proposal about how to combine grammatical, symbolic, hierarchical representations with deep learning. You can think of this as a symbolic tree generation process with neural control. And we will look at how this and ordinary sequence-based LSTM models perform in a number of controlled syntactic tests going forward.